In standard large language model deployments, the system generates text and then stops. The transition to agentic workflows occurs when that same system branches into a network of subtasks to achieve a specific objective. This moves the architecture away from the conversational chat window. Enterprise operations require a headless, multi-step system where specialized workers coordinate in the background. Consider a common e-commerce workflow, the automated refund agent. To resolve a request, the system must read a return policy, verify the order in a secure database, and trigger a payment API to return the funds. Granting a generative model direct access to a payment gateway creates significant risk. A system designed to predict the next token in a sentence can easily hallucinate a policy exception and execute an unauthorized transfer of funds. Moving from an AI that answers questions to one that executes transactions requires a physical separation. The intelligence layer that plans the task must be decoupled from the execution layer that carries it out. The consequences of running agents without this separation were demonstrated by the OpenClaw vulnerability. Over 28,000 systems were exposed when agents were granted unrestricted admin-level access to sensitive databases. This failure highlighted the risk of identity sprawl. Currently, 77% of enterprises lack the tools to inventory or trace the actions of non-human entities operating inside their proprietary networks. Safe production deployment depends on 4 infrastructure pillars: sandboxed code execution, rigid security guardrails, cost latency optimization, and rigorous evaluation protocols. Without the verifiable infrastructure to govern these actions, the underlying intelligence of a foundation model cannot be safely utilized by an enterprise. The baseline for any execution layer is isolation. Autonomous agents cannot be permitted to run native code directly within the core application environment. Instead, the orchestrator delegates a task like issue refund to an isolated, serverless environment. AWS Lambda or Google Cloud Run provides the secure sandbox to handle the actual transaction. Historically, this created an integration bottleneck. Every new AI model required custom connections for every database or SaaS tool. The Model Context Protocol, or MCP, provides a universal standard. It standardizes how AI systems interact with external data sources. MCP securely routes the execution command from the reasoning model to the Stripe payment API. Sandboxing combined with MCP ensures that the agent's operational scope is strictly contained. Even a hallucinated command remains trapped outside the primary application. In a multi-agent topology, individual sub-agents operate within a chain of trust. The risk arises from permission hallucinations, where a temporary agent mistakenly assumes it has the authority to delete files or move funds. To address these risks in critical infrastructure, the U.S. government established the 2026 NIST AI Agent Identity Guidelines. The framework mandates zero trust for non-human entities. Every autonomous action must be backed by a verifiable digital identity. This identity is managed through an agent passport. The credential identifies the agent's origin, the human principal responsible, its permitted scope, and its time to live expiration. Our refund agent presents this passport to prove it is restricted to a $50 spend limit and a 4-hour operational window before it self-terminates. Cryptographic identity provides the only viable security model for an interconnected network of autonomous agents. Running multi-step workflows through a single massive foundation model is inefficient. The sequential processing leads to high API costs and significant latency. To minimize delays, systems utilize contextual routing and task decomposition. The orchestrator divides the goal into parallel actions. It routes the document check to a focused RAG agent to retrieve the policy. Simultaneously, it routes execution to a dedicated code agent for payment logic. Checking the policy locally via Vertex AI search grounds the agent in the correct data without burning expensive tokens on the primary orchestrator model. Routing by domain expertise is the only viable way to scale these operations across an enterprise. Validating a production-bound agent requires more than simple text prompt testing. Developers must use rigorous execution tracing, running agents through cloud simulators to map every decision pathway. This execution trace audits the refund agent. The log proves it first retrieved the return policy and only subsequently requested the payment tool. This deterministic sequence must be verified before the agent is granted access to live systems. These evaluations are the final gateway between an experimental model and a production-ready digital worker. Beyond a single refund agent, we are looking at an ecosystem of millions of specialized agents interacting simultaneously. Deploying these systems at scale requires solving an engineering problem of verifiable infrastructure, moving the focus away from the underlying intelligence of the model itself. Integrating sandboxing, passports, and contextual routing creates a functional framework for deploying digital workers across a global network. Standardized hubs like AIagent.org and open protocols like MCP provide the critical architecture to scale this network safely. Trust is the baseline for the agentic web. The platforms that architect that trust will govern the foundation of the new digital economy.